In this video, we are going to continue our discussion on section 4.3, fractional exponents. In video 1, we focused heavily doing 2 examples on eliminating roots, and we are going to continue that with our example number 3. Please note the directions. Solve using substitution. I would like to emphasize, yesterday we saw that this is a type of problem which could be written to isolate the square root. After isolating the square root, we saw that you could square both sides, obtaining this by expanding it outward. We would then get x squared minus 4x plus 4. Grouping all our like terms together, we then got 0 is equal to x squared minus 5x plus 4, which sets up something that would fit the quadratic formula, or possibly something that we could factor. Well, instead of using the quadratic formula for this one, I would look at two numbers that multiply to positive 4, but those two numbers add up. They sum to negative 5. Negative 1 and negative 4 comes to mind, so this would factor to give us x minus 1 and to give us x minus 4. Applying the zero product rule, we then get x is equal to negative 1, or x minus 1 equals 0, or x minus 4 equals 0, which gives us the solutions x is equal to 1 or x is equal to 4. That was our technique from yesterday, and you'll know I rushed through it fairly quickly. Because of the directions, this would be considered a wrong answer. Even though everything is correct, and we have our solutions of 1 and 4, which, by the way, we would still need to go back and verify that we don't have an extraneous solution. I'm not going to use that technique because we're not allowed. We did not use any substitution in that problem. And the directions specifically say solve using substitution. So what is this substitution strategy? It's a different way of getting rid of the square root. One thing we could do is a change of variables. Well, what's your favorite dummy variable? Give me a letter. P. All right. We're going to let P be equal to the square root of x. Please notice then that tells us P squared is equal to x. This is where we get the substitution. By plugging in these new variables, this problem is 2 plus p equals p squared. Simply rewriting it then gives us p squared minus p minus 2 equals 0. You notice that this got us to the quadratic formula problem pattern much more quickly than the last technique did. It just gives us another way of doing this. It's another strategy we can use. Both of them are valid, and so for the most part you can pick and choose which way you want, unless the directions specifically tell you to use substitution. Well, in this instance, we would have to recognize that negative 2 and positive 1 are the factors which give us solutions. P is equal to positive 2 or P is equal to negative 1. Well, consider what this is telling us then. 2 is equal to the square root of x, or negative 1 is equal to the square root of x. Tell me what you think about those potential solutions. Square roots are positive. Since the square root refers only to positive numbers, it can't equal -1. Coming back to the top one, if we square both sides, we get 4 is equal to x. And we're able to eliminate the extraneous solution also. We're done, getting the same result as we did last time, just a different strategy. I would like to ask you, though, which one do you think is better? What is your preference? All right, this particular example I did not have pre-planned. The students said they would like to have another example using this substitution strategy, so I made one up. Also pointed out in class, unlikely to have it work out to be a nice, smooth, even number. We'll probably wind up with a square root answer. The strategy behind this is still to eliminate the square root. We don't want square roots in here. So what we do is a change a variable into something like this. That way, what we can do is take this entire section right here, and it will be replaced with just a plain letter. Generally speaking, that's considered simpler and easier because the square root is now gone. It also introduces the problem now that we have two variables, a variable p and a variable x, still in this top equation. We have to get rid of the x also. So I need something of the form x equals blob so I can make a substitution for that x. That's why I will have to do some solving here. P squared is equal to x minus 5 because I just squared both sides of that equation. Adding 5 over tells me p squared plus 5 is equal to x. And now this is something we can substitute in here, getting p squared plus 5. This is why it's called the substitution strategy, because we're doing a change of variables to make substitution. To make a substitution. Now that we have this problem, oh, what do you know? This works out pretty nicely. We have to solve the problem. Well, we can subtract off 5 from both sides and get p is equal to p squared, which is p squared minus p equals 0. If we factor out the p, what gets left behind? And so using the zero product rule, p is equal to 0, or p minus 1 is equal to 0. And we have two potential solutions. Kind of cool that it worked out and we didn't have anything too crazy with square roots. But now we still have to determine, do these things make sense given the context of the original problem? Remember, the original problem let me bring this back up. If p is equal to 0, this tells us 0 is equal to the square root of x minus 5, or 1 is equal to the square root of x minus 5. Well, this tells us 0 is equal to x minus 5, so x equals 5 is one potential solution. This would tell us 1 is equal to x minus 5. Squaring both sides, 1 squared is still 1, which tells us x is equal to 6 for a potential solution. We still need to verify if either of these is an extraneous solution. We still need to plug them back into the original and see if they actually check out. So, 5 plus square root of x minus 5 equals x. Let's try plugging in x is equal to 6, x is equal to 5. If we plug in 6 minus 5, is that true? 6 minus 5 is 1, and the square root of 1 is just 1, so yes, this one checks out. Let's verify the other one. 5 plus 0 minus, it's 5 minus 5. So 5 plus the square root of 0. That will also work. So in this instance, we check to see if we have an extraneous solution, and we don't. We know these processes many times will create a false solution. This one didn't. All right, continuing. Where are the points on the line y equals x, which are 5 units away from the point 3, 4? In this particular problem, we need to consider a couple of things. Most notably, we are given this component 5 units away. That tells us its distance. And we have distance from a point. Well, since we're focusing on distance, we would have to employ the distance formula. Well, which pieces do we know? Which pieces can we plug in? Well, we know the distance is equal to 5 because it's 5 units away. We know the x-coordinate, x1, is equal to 3. We know the y-coordinate, y1 is 4. And so we have all of this information. But there is still one more piece of relevant information here. We are looking for the points on y equals x. And so we can replace this y with x. And we now have something we can solve. Squaring both sides gives us this information. And we can continue this by expanding each one of these. Here we'd have x squared minus 6x plus 9. Expanding the x minus 4 quantity is x squared minus 8x plus 16. And we now have an equation we could solve. Let's start by combining our like terms. X squared plus x squared is 2x squared. Minus 6x minus 8x negative 14x. 9 plus 16 is 25. And so we now need to solve this quadratic. And so what we'd wind up with, subtracting off the 0, we'd have 2x squared minus 14x equals 0, which again was obtained by subtracting the 25 over. 25 minus 25 would be 0. If we factored out a 2x, x minus 7 is left behind. Employing inverse reverse, employing the zero product rule gives us 2x equals 0 or x minus 7 equals 0. Allowing us to finish it off and get these two solutions.
Thank you.
All right, and our last example for this particular video. Find all the points that are equidistant from 0, 1 and the line y equals negative 1. Now, if you find this particular question confusing, I would suggest you do some YouTube searches about focus, directrix, parabola. And I'll write those down so you would know the keywords on what to search for. This is a problem that's related to these three things, and so there are a number of YouTube videos that provide greater depth and greater clarity explaining this process a little bit more. Okay, first of all, we should try to understand what's going on in this problem. We are working in the coordinate plane. We have the point 0, 1. We have the line y equals negative 1. Okay? What we are searching for is an equation that tells us how to find points that are equidistant between the two. Now, for instance, I'm just going to make up this piece and say, here is a point right here. Well, this has a distance right there, and it has a distance right here. Are those two distances the same? Clearly not. So this is an example of a point that does not fit the criteria. We are searching for a point that actually balances these two things out. For instance, if I came downward here, that gets a little bit longer. Do we now have two distances balanced as the same? Not quite closer. What we're searching for is every single point that actually creates these. Well, the end result answer, cutting to it, basically just cutting to the chase, because we don't have the tools to physically create one of these, at least we don't have it present with us, we will wind up having a parabola get created. This parabola, if we went distance and distance, those two things would be the same. If we came over here, those two distances would be the same. Every single location on the parabola, those two distances match up with one another. This is a problem where we are trying to create the equation for this parabola. The vocabulary here is not important for what our focus for our topic, but this point is called the focus. This line is called the directrix, which is why I mentioned there are YouTube videos that explain this particular thing. But they go through basically the same process as what I'm mentioning here. The key feature we have to have is that there are two different types of distance. We have a distance from the focus to the parabola. That will be distance type number 1. It needs to be equal to the distance down to the directrix, which is distance type number 2. We need to create an equation for distance 1 equals distance 2, because that's how we get our criteria of equidistant. Where do those two things come from, though? Well, what is the distance here? If this is the point xy, what is the distance? This particular section right here is just y, because it's the height above the y-axis. But you also have this little section of 1 downward. So this distance here is simply y plus 1. On the other side, we need the distance located here, which we will note we would get by employing the distance formula. This is distance from the point xy to 0, 1. At this stage, creating the D1 is pretty much the same thing that we did here. We would create and say that that distance is x minus the x coordinate plus y minus the y coordinate. Just plugging things into the distance formula. And we have now created an equation which we will conduct some algebra on to simplify it. First things first, I want to square to get rid of the square root. Squaring both sides gives me this. And what we would like to do is to manipulate this to create something of the format y equals blob. So our next step is to expand those two exponents, x squared plus y squared minus 2y plus 1 equals y squared plus 2y plus 1. We can now combine our like terms by subtracting off y squared from both sides, which cancels. We can subtract 1 from both sides, which cancels. And we could add 2y to both sides, giving us x squared equals 4y. Thus, y is simply x squared over 4. And we have created the parabola, giving us an equation which we could plug into our calculator and know that this is actually equidistant between the 2 points. At this point, we'll stop the video at 25 minutes and observe that was basically this one objective. Being able to apply distance formula in the plane